All right. Hello, everyone. This is your host, Nagu. Welcome to the program. Before we get started, today's session will be recorded and the slides will be shared later in the channel. And we'll be monitoring, watching the channel for any questions. So please feel free to fire away your questions. Without further ado, let me welcome Ali, our founder of yAcademy, to get started. Ali, it's all yours.
Thank you so much, Nagu. And yeah, welcome everyone to zBlock2, our longest fellowship to date. And also the fellowship where we received the most applications. You may have noticed that we were like, we went over the deadline by like a week. We actually received hundreds of applicants, so we wanted to be to give every application the attention it deserves. So yeah, this is exciting to kickstart. First, I would like to introduce the residents who will be basically your shepherds throughout the fellowships. Nalati, Igor, Ulba, Nagu, our host today, and Parsley. So these excellent people are ZK auditors themselves, and they will be working alongside of you. They will teach you, but they will also, I'm sure, they will learn from you as well. And you will see them on Discord a lot. I'm also happy to welcome the Suma team, who are the code base authors of the SOMO protocol, the protocol that that is the subject of our fellowship. Enrico is the lead dev there. Actually, Enrico, I met Enrico at DevConnect, and he has a very calming presence about him, which is very, very useful when dealing with ZK. ZK can be intimidating and unnerving, so having that vibe is really good. So Enrico is very helpful and very excellent person. Okay. I will give an overview of the fellowship overall. This one, as I said, is the longest fellowship we have done. So it is slightly different, but in some ways it's also the same. It's not so different from what we have done before. Yeah, we estimate that we need at least 3 months. We wanted to have ample time for everyone to digest the code base, for everyone to take their time, taking a crack at maybe some bounties or something. So we did not want time to be an issue. So that's why we allocated 3 months for it. If needed, we did mention that we may extend it by 1 more month, but we will see how that goes. I think 3 months will probably be sufficient, but if need be, we can push it to May, basically. Soma will be our main focus, as I said, and the fellowship basically comprises of overview sessions. These will be over the first 2 weeks. So over the first 2 weeks, the Soma friends will be talking the most. Introducing the protocol first, and then the code base, and then the smart contracts, the verifier, and so on. There will be office hours throughout. Obviously, these will be announced in advance. I am thinking this time we will ask everyone, because we don't know where everyone is in terms of progress. We don't know if questions are accumulating in people's heads. So we may ask, hey, we could have an office hours at the end of this week. React with thumbs up if you do have questions that you would like to discuss in sync, because sometimes it's easier to say, for example, ask Enrico to share his screen and put something to the code base and to answer a question. It's much easier than doing it async. Obviously, the main discussions will always happen on Discord. Right now, we have the main Suma channels, but there will be other channels as we probably break into groups in the weeks ahead. One of the residents will talk to you later on about working in groups and how that will work. And then obviously the fellowship leads to a collaborative writing of a final report. Don't worry, you're not going to be asked to, fiddle around with PDFs or anything like that. No, it will be very easy for you. Your issues will be logged as GitHub issues, and then the residents will take care of curating that into a final report obviously with attribution to everyone who contributed to it. And throughout, we will have retreat talks. These we are not prioritizing that much this time around, but every once in a while, it's good to just sit back and listen to an expert talk about something general, not too heavy technically. The technical talks, we are prioritizing this a lot in this fellowship. So these will be given by the presidents. Maybe they will give 1 or 2 sessions each, and they will be like, we want them to be like this bottom-up, modular, bite-size kind of talks where we attack a single thing. We don't care about covering so much. We just want to understand a single thing and understand it really well. And we will have the first of those next week in between the overview sessions of Suma. Our residence Nullity is going to kickstart that with the first talk on Halo 2. So these are basically the activities that you expect to see in the next 3 months or so. And this is the general flow, basically. This is how, what it will feel like in the first 3 weeks. You guys are listening, learning, digging, trying to make things, trying to formulate non-trivial questions. As we mentioned in the applications, and generally, if you have been around yAcademy, we have this trial by fire sort of ethos, which basically means fellows are expected to catch up and on their own, and it's only really it's that last mile that we try to step in and push you over the hump, basically. So yeah. In weeks 4 to 8, you will have had hopefully a decent understanding of the protocol and the code base, and you will have more deeper questions, but you will also find yourself wanting to maybe break into groups, work in pairs. You may have met someone that you guys are working well together, and you want to do your own thing on the side, sort of. You may find yourself wanting to share something, either you or the two of you, after you have formulated it into a coherent gist or a session, if you want. So in the middle, basically, fellows tend to be louder. And then at the end, things will get quieter. You will be validating issues, writing the report. Maybe you will have some back and forth discussions with the residents or Enrico about the validity of certain issue. If you have worked throughout the fellowship on some sort of output, let's say a gist, an article, or a session, or something like that, or some tooling, then this will also be the time for you to polish it up before we publish everything that comes out of the fellowship at the end. Which brings me to the bounty program, which is related to some of the activities that I was talking about. So we are going to award, retroactively, we're going to reward proactive effort. So if we spot someone doing something useful and interesting and thoughtful, we will be handing out bounties at our discretion, basically. So we do encourage you to keep that in mind. We also do encourage you to think about tooling in general. Tooling for auditors, basically in the ZK space, it's still very nascent. It's not that mature, so it's helpful to create tools in that regard. Anything that help comprehend and analyze the code base, that whole category, basically. If you are into that and you make something useful there, and we spot it, we will definitely be generous there with our bounties there. So these are initiatives you can take on your own. You don't have to ask for permissions or anything. And then there are bounties for specific bounties that we will explicitly announce, similar to the fun bounty that we did this week about a question per day. So we may ask for a specific a tool to do a specific thing, or we may have some challenging puzzles throughout, things like that. So the whole point really of all of this is to, or the reason why we do that is to incentivize teaching, because teaching is indeed the best way to learn. If you find yourself on the line and you have to explain something clearly to someone, you will find that your own understanding is being tested and it's being sharpened and improved. So we really do focus on this idea of learning by teaching, sort of. And no matter what you're doing, whether you are like digging into the code or whatever it is you're doing, if you formulate what you have learned in a coherent way, you can basically easily share it with others. So keep that in mind as you go about learning. Yeah, so these are some pro tips. I'm sure you can read them. Basically, don't be shy, but at the same time, I want to emphasize the requirement that discussions needs to be high signal. So please don't ask like trivial questions, things that you can find out on your own. And also, when there is a discussion, try to pause, think before you contribute to a certain discussion, to try to keep it as high quality as possible. And do make use of threads. If you find yourself in a back and forth with someone and you guys have not succeeded in convincing each other, maybe take it into a thread, just so that it's organized. Okay, so any questions so far about the fellowship structure and all of that? Okay, excellent. If there are no questions, that means hopefully everything is clear. Or maybe you guys are shy, but please don't be, especially in future sessions. Feel free to ask questions. Okay, so today I'll just end up with a quick sort of recap of actually something we started in the last fellowship, something we have been calling ZK in context. It is a way for us to try to allow someone who does not come from CS background, may not even have that deep of a software engineering background, to as quickly as possible understand where this prover verifier model works. So obviously there's a lot of amazing materials, introductory materials out there about ZK, and those are extremely useful and helpful. But if you have absolutely no background in CS at all, you may still have this lingering childish, not childish in a bad way, but childish as in wondering question: where did this thing come from to begin with, like this prover verifier model? And it wasn't actually born recently or in the past 10 years. Computing in ZK has been known since the 80s, actually. It's only recently that some advances made it extremely practical from an engineering point of view. So the prover verifier model is started as a computational model, as something like the an equivalent or a different way of solving problems, abstract problems, a different abstract model, just like the Turing machine or something else, basically. But then over time, it wasn't practical enough up until 2010 or so, but then it started becoming extremely practical. And that's, if you are familiar with the recent advances, that's when it started getting applied in blockchain space and so on. So just to what I would like today is just to give you the beginning of a thread that will hopefully incentivize you to go and dig deeper, basically, into this context that we provided, and also look at the materials that we shared in the library. So look at the following problem. You have a graph, and you want to distribute colors so that adjacent nodes have different colors. So, for example, this is an invalid coloring because these two have, they are adjacent. There is an edge between them, and it's the same color. So that's like invalid. But this is a valid coloring. All adjacent nodes have different colors. So this is a computational problem, and if you with some materials I will share at the end, you will know that when we ask a computational question like this, does this graph have a valid coloring? That statement is actually a mathematical statement that is either true or false. Meaning, computation is fundamentally is precisely the notion of mathematical truth in the classical sense of the word. So what happens when truth is expensive? When we're trying to find out if something is true or false, and that is extremely expensive, like this case, for example, does this graph have a coloring? If the graph is extremely large, knowing that truth is extremely expensive because we don't know of a smart way of solving it. The larger the graph, the more exponential the effort needed to decide, quote unquote, decide that truth, basically. But the interesting thing is that problems like this, verifying a claimed coloring is easy, even the graph is extremely large. Like the graph doubles in size, the verification of a claimed coloring doesn't go 2 to the power, it doesn't go 2 to the power some function, it doesn't exponentially grow, it just doubles as well. So it's linear alongside the problem. And this claimed coloring is what we call a witness. And you may have heard of the word witness in the context of zero knowledge. And it actually originates from this. It originates from a solution. A witness is a claimed solution to a computational problem. And computational problems are nothing but mathematical or claimed, supposed mathematical truths. So suppose we let's see if we can come up with a way to solve this problem in ZK, meaning convince someone that this graph has a coloring, a valid coloring, without actually revealing the entirety of the coloring itself, because that would be, you can imagine, that would be a very valuable secret, let's say. So suppose the prover draws the graph on a massive football field, let's say. Just imagine. And then the prover solves the instance. So they claim that they have solved it. They claim that they know a solution to the coloring. And they do indeed assign colorful balls on each node. But then they cover each ball on each node in the field with a cone. So right now we don't see the solution. The solution is hidden. And at that moment, you, the verifier, you enter into the field and you select a random edge, okay? And you ask the prover to reveal the colors of the two nodes of that specific edge. And you verify that indeed they are different. The colors on these two. Every other node is now covered by the cone, but at least for these two that you have chosen, they are different. And now you exit the field. Now, do I say, okay, I only saw one edge? The prover could be lying. There could be two adjacent edges somewhere, two adjacent nodes out there, and they have the same color. I only checked one. Well, indeed, that is true. And the probability that you have caught him lying is 1 over the number of edges, basically. So it's not a great probability. He could easily have cheated. So we have two opposing, let's say, requirements. You, the verifier, you want to increase your certainty that the coloring was correct. At the same time, the prover doesn't want to reveal the coloring overall. It's like a trade secret or something, or they want to sell that solution, or they want to keep it private or something like that. So what happens, what the prover can do is they can permute the coloring. So after you exit the field, they would switch, or they would swap every red. They would swap every red to green and every green to blue and blue to red, for example. That's one permutation. So they sort of like shoveled the solution. It's exactly the same solution. It's just that they swap the colors, which doesn't affect the solution if they indeed have it. So they shovel it around and they cover them again with cones, and you enter and you pick a random node and they reveal that node. You go out, they permute, they shovel the solution by changing the colors, and you enter again, and so on. So you can repeat the steps from 4 to 7. You can repeat it k times. And the more you do it, the more you do this, the more likely that you would catch a cheating prover, the more likely that your random choice of an edge would stumble upon one that was incorrectly colored, basically. So if you look at step 3 and 4, this is where the prover covers each ball once, and then you enter the field. Sorry, when the prover covers each ball, this corresponds to a commitment scheme that you might have heard of, like the polynomial commitment schemes. It's a way to bind the prover to their claim so that they can't bait and switch, basically. And you entering the field and exiting the field, that is the interactive communication that happens between prover and verifier. This is something you may have heard of. And by the way, what I'm describing here is indeed a real zero-knowledge proof. In fact, it was the very, very first, I believe it was the very first demonstration of proving something in ZK. So this problem, this 3 coloring problem, is what we call complete, NP-complete. It is complete for an entire class of problems, meaning if you have an ASIC that can be used to solve instances of 3 coloring problem, then any problem in this entire class of problems we call NP. If you don't know what that is, don't worry about it. I'll share some materials to know. But basically, think of it this way: if you have a machine that can solve this 3 coloring problem, you can solve a huge class of other problems by compiling into a machine purposely built for this 3 coloring problem. It is complete for an entire class, basically. And that entire class is sufficient for a lot of purposes. It's certainly sufficient for, let's say, blockchain purposes, right? So if you do have a machine for that one, you have quite a lot of power. So if this three-color problem is complete for a large class, and we have known for a long time how to outsource its execution to someone, trustlessly to someone, without actually having to do the expensive solution ourselves. Remember, I said the three-coloring problem, um, there is no other way, there is no easier way to solve it except trial and error. There is no way to, there is no smarter, quick way of solving it. But if this is the case, then why don't we have ASICs for the three coloring problem, and we compile into them, and we can do our computing generally in our daily lives using this model? Because we can get this, this trustless paradigm, which is extremely valuable for both parties, for the prover and the verifier. And the reason is because K, remember we said you have to repeat this K times. So, you need to repeat this K times such that this probability of catching the prover is high enough. K is large. It has to be much, much larger than the number of edges. And the witness size is linear. The witness, what is the witness? It's a list. You can think of it as a Python list, and it contains tuples, node, color, and so on. That's what the witness is. It's an assignment of nodes to colors. And it's linear in the problem. So it's not exponential. It's not extremely huge, but linear is still not cheap enough. It is not cheap enough to make this whole decoupling of computation between search and between verification worth it. It's not really that worth it. This whole paradigm is only useful and attractive when the asymmetry between proving and verification is extremely big, right? That's when things become sort of attractive. If you think of it, just to give you like a more concrete sense of what we're talking about, if you think of it in the context of the blockchain, when the witness size is linear, that means if someone implemented a three coloring based ASIC to prove the execution of the Ethereum blockchain, the historical execution of the Ethereum blockchain, the witness that would have to give, that's the verifier on their phone, for example, would have to hold in their memory, would be equivalent to the size of all historical blocks, basically, at least at a minimum, basically, which is still, it's still big and cumbersome, basically. So to make this model more attractive, we needed to eliminate interactivity, reduce witness size, reduce verification cost. And over 3 decades, late 80s, 90s, and the early 2000s, this sort of what was happening. There was a soup of extremely active but complicated research under the PCP theorem research that tried to do exactly this. There wasn't much progress, but then in 2010, 2013, big cracks started to appear, and we finally began to have proof systems that push the witness size and the verification cost, and obviously eliminate interactivity. This is eliminating interactivity is done by the FT transform and all that. So there was a lot of advances that needed to take place for this computational model to begin to be practical, basically. And in all proof systems, the fundamental thing that needs to be done before all these tools can be applied, you need to reduce your computation into an equivalent representation of polynomials. So reduction is compilation. You are you are familiar with the notion of reduction more than you think. If you have compiled any code, what you're doing is basically reduction. You are reducing something from English, that's the intent in your head as a programmer, to something in, say, Python and or C, and then the compiler will reduce that into assembly and so on. So you can think of the system of polynomial as just another compilation target. And it's on these polynomials that these complicated tools, cryptographic tools, mathematical number theoretic, and abstract algebraic tools are applied in order to have all these goodies, basically. And you can think of the circumcompiler as such a reducer, basically, and Halo 2, which is more theoretically more powerful than Circom, because you can quote unquote decide problems in more classes than you can do with R1CS based like Circom. So what I talked about today is just hopefully a motivation for you to, if this is all new to you, if you come from CS background, most of this seems, or most of this is known to you already. But really my motivation is to nudge you into thinking about the notion of computation itself. And as I said, you should be motivated in thinking about notion, because computation is precisely the notion of mathematical truth. And that's why the foundation of computer science in the 30s happened at the same time that people were trying to find a solid foundation for mathematics itself. And then the notion of universality. Can we do any computation out there? Are there computations that are beyond proving? Are there computations that are beyond algorithms and things like that? So possibilities and lack thereof. And then from possibilities and lack thereof, here in the universality of things, you can think about the cost. So you delineated the set of problems that are in theory possible to solve. How much does it cost to do them? So here we talked about possibility and impossibility. Here we're talking about intractability and lack thereof, and cost, and so on. And having these three, having the context from these three foundational stuff will hopefully allow you finally to understand where arithmetization, which is at the heart of all zero knowledge proof system, where it came from, what it means, why it works, why it makes sense on a fundamental level. If you look at that series that I shared here, we stopped basically at the, we arrived at the R1CS arithmetization, which covers a large class of problems that we call NP complete, but there are problems outside of this class. And they are not really that important in practice. In practice, if you have a machine that that decides the class NP, you can do basically almost 99% of things, but it's still very, it would be very good for us to also reason about problems outside of NP, what it means for a problem to be outside of NP, and so on. And that will hopefully give us an idea of why Halo 2 is a different animal from circumcompiler, and a much more powerful animal, basically. So yeah, this is all I really wanted to talk about today. Is just basically, hopefully, a motivation to get you started there, and to hopefully also motivate you to think about these things in a more let's call it foundational way. Like, you should not shy away from having childlike questions like, what does it mean? Like, verify, where did this come from? Why does it make sense on a fundamental level? And things like that. And that's not gonna make you understand the entirety of ZK. That's not really the whole purpose. This specific tools from these cryptographic and mathematical toolkits that are used after we have reduced the polynomials, that's where most of the difficult stuff are there. And the idea is not that you are going to begin to have magical powers to understand each one of them quickly, but at least you will know where they fit. You will be in the kitchen and you know that this fits in this cupboard. This is a knife, it's a sharp knife. I have never used it before and I'm not skilled at it, but I know what it's used for and I know that it belongs in this spot. So I'm gonna put it there until I'm ready and so on. So it sort of helps you understand why something should work, why ZK should work in the first place, and where everything belongs, basically. And in your mind, you should always you should always know where you are, whatever you are reading or looking into. Are you in the reduction phase? Are you in the phase where we're taking computations and trying to reduce them, compile them into polynomials? Or are you in the steps that happen after we have populated these polynomials? And yeah, and then understand that, you know, the cryptographic and abstract algebraic tools that are applied on these polynomials, they are usually interchangeable. You can swap something for something else. You can swap, say, sum check for a polynomial commitment scheme and so on. And usually when you hear branding in proof systems, you hear people talk about different brands, Plonk, Turbo Plonk, Ultra Plonk, things like that. It's usually because they have swapped one of these tools, or they have created a different recipe from these tools to basically create the entire ZK snark protocol that they are talking about. If this is all confusing, don't worry about it. If you go and watch these, you can ask questions later. We'll be happy to engage with them. But hopefully I gave enough for you to motivate you to begin to think about it in this way, which hopefully also makes sense as well. So yeah, I am happy to take any questions about this specific part or any questions about the first part of today's talk about the fellowship generally before we close. All right, so I guess no more questions. So Nagu, you are our great host. I am going to throw things back to you.
Great. You can also ask questions in the channel if you are shy to speak on the mic. Oh.
Excellent. So yeah, I guess Nagu, we have our next sessions on Wednesday, right?
Correct. Yeah. So we have next week. Our next session is on Wednesday, same time. And
there's just two questions in the chat.
Oh, there's a question in the chat.
Yes.
Let me read the question. How is ZK audit process different from Solidity?
I would probably throw this at one of the residents. Probably they would know better, but obviously, in general, the prover side of things, it's much larger and much more complicated. And one of the reasons why proof system code bases right now, if you're dealing with a ZK-based applications, for example, is because the the abstractions are not fleshed out cleanly yet. The separation between, we are still too close to the polynomials. Let's put it this way. But over time, you can expect more and more abstractions to be layered, such that the final ZK application is quote unquote small, in the same way that any other applications that you do in Web2, for example, is small. You know, you just import a bunch of stuff and you're just focused on the application logic. This is actually already kind of true with Suma, basically, because they are harnessing this huge Halo 2 code base that is already done. But it's fresh. It's still super fresh to the point where we, as auditors, we still need to look under the hood a little bit. And so this challenge, I think, is transitory. Say 5 years from now, let's say Halo 2 has been solidified and being used everywhere, and a lot of people audit it over and over. If we get the next ZK app in 5 years and they build on top of it, the auditor may not have to look at Halo 2 because it has been battle tested a lot. Not only that, but also the separation, the abstraction is much, much cleaner, basically. But here, as you will see when we look at Zuma, we are still dealing with lower level stuff like chips, things like that. So I would say this is sort of generally at the moment the difference in challenges between ZK and Solidity.
Yeah, I think I kind of agree with Ali on this too. We are so early in this ZK security space. The process-wise is probably similar. You know, we're trying to find bugs in some software code, but the underlying computational gadgets, the computational blocks are very different. So we don't really know how to look at them systematically. You know, now we know how to automate a lot of stuff and how to find bugs in Solidity. You know, there are at least like some repeated abstract patterns that we can rely on. But in most of ZK, we don't really know. Everything looks pretty new, brand new. So there's a lot more learning to do, a lot more discovery process we have to do. So we have a couple of more questions. We can take that. Let me follow up with the next question. When auditing ZK, is it more important to understand the fundamental math of the protocol or the implementation in Halo 2?
Yeah, that's a good question. So obviously, as an auditor, the lower down the stack you can go, the better, and we'll try to push ourselves and push you guys to go as low as possible here. But I would, well, it depends, because there is math everywhere here. So it depends on which math you're talking about. If you're talking about, let's say, an elliptic curve and its properties, has it been audited and things like that, that's, you know, that's at the lowest level, for example, and probably a level that we will probably not get into. You can also talk about one level higher about the arithmetization of Plunk. That's what Halo 2 is. It's an instantiation of Plunk's arithmetization. Are we going to audit the mathematical proofs in the original Plunk, for example? You guys are encouraged to, but we'll see if we get there. So I would say we are at the, you should understand, definitely understand, let's say, the permutation argument in Halo 2. That I would say when you get to that point, then, if you get to that point and you are able to verify, that's a good sort of like level. But the most important thing, I would say, is to understand which math belongs where. So there is a math concerning the phase where we reduce a computation to polynomials. That's complexity theory math and all of that. And then there is the math that happened after that, basically the polynomial commitment and the argument of knowledge, the IOP. That's the complicated stuff, basically. So if you get to the polynomial commitments and understand it and understand the permutation argument, that's already great enough, I would say. So to answer the question more briefly, understand as much as you can from the math, but at the very, very least, understand which math belongs where and why it works on an intuitive level. At the very least, you should have that in your head.
Great. Let's go to the next question. This is from Sebastian. In the tree coloring problem, if the balls were changed continuously, doesn't it break the commitment?
Yeah, good question. So let's see. Let me go to all the steps. Yeah, so when the prover is committing in step 3, when they are covering the balls with a cone, so they are committing to the solution. They can't change it anymore. You enter the field and the cone is on top of all the solution. What's happening, I think what you're thinking is, when we are permuting, where's the permuting? Yeah, when we're permuting the solution, that's not changing the solution. You are only permuting the color of the balls. So basically, how would you call it? You're just swapping red for green, green for blue, and blue to red. And if you do that, if you permute all the colors, then the solution is fundamentally still the same. You just change the colors on the ball. So the commitment, if I understand the question correctly, the solution is exactly the same in every time. The same as in the possibility of it is the same, but the colors are just being permuted. To make it even easier, think of it this way. In each exit and re-entry, instead of red, green, and blue, the provers exchange that with totally 3 different colors, basically. So yellow, violet, something else, let's say. So if you think of it this way, every time they are using 3 different sets of colors, basically, the solution that they found is still fundamentally the same. Is this just this cosmetic, but fundamentally essential thing that they are doing to keep the privacy of the solution that is changing? So yeah, it's one solution. There could be multiple coloring of the same graph. That is also a possibility for sure, but they are usually not a huge number. They are not like infinite or anything, no. But it is possible in theory to have multiple solutions, which as a verifier, you don't really care about it. You just care about whether there exists a coloring. If now, this is actually an interesting thing to think about. If there are multiple solutions, and every time, let's say the graph is the number of stars in the universe, and the prover claims to have, let's say, 2 to the power 10 number of solutions. not claiming, but they hold it in secret. And every time you exit and come back, they are actually committing to a different solution from the set of all those valid solutions. Does that change? Does that change your confidence in what they are saying? That is, yeah, that's an interesting question as to, well, you will know at least that they know at least one correct solution, so that's for sure. But if they, let's say you're saying, let's say they claim to know 10 solutions, but none of them is actually correct. All of them are 99.9% correct. You will indeed eventually catch them lying, because you're going to have to do this k times, and you can in advance work out what this k should be for you to catch them with probability 99.9999. So it's this k that is going to be your safeguard, basically.
All right, let's go to the next question. This is from Flying Nobita. From what I understand, there's different auditing techniques. For example, formal verification methods that includes fuzzing, static analysis. Would we be focusing on a specific technique? Does anyone want to take it?
Yeah, probably one of the residents can chime in on this. But I would say, I mentioned very briefly that the tooling there is very immature. That's one of the reasons why we're incentivizing you guys to with these bounties. So if you find a way to do some sort of fuzzing or auto analysis, that would be great. I do know that there are teams teams that have, I know at least one professor, I can share their research papers that try to do auto analysis of zk code bases. But I would take that with a grain of salt, because it's complicated enough for regular, let's say, easy code bases, quote unquote easy, let's say Solidity or something, to create formal verification stuff. I personally favor fuzzing over automated analysis. So the question is, yes, you may use those, but there aren't many to begin with. You could be the first one to actually create something interesting in terms of fuzzing zk. I'll throw the mic to the residents if they have any opinion on this.
Yeah,
I think from
agree
my
with
point
that.
of view,
Mm-hmm.
sorry,
ahead.
carry on. You're more than welcome.
Uh-huh.
No,
I agree
Nobility,
with
you have
you.
more. Go.
Yep. I think we will be using very Halo 2 specific tools. I think Halo 2 has a pretty complex structure compared to CIRCOM, and we might be developing those tools. There are like 2 tools right now. We would try those, and I don't think there are a lot of formal verification tools. So yeah, we'll be doing a lot of manual auditing instead. So yeah, we might be developing, and a lot of focus would be doing it manually. Mhm.
Agreed. Yes, that was what I was going to say. Sorry, Nagu, just to mention, we did miss a question slightly higher up from Hamid. And his question was, how deep into Rust should we go?
I think, in my opinion, there is no limit how deep you can go. But we are time constrained, and also we have certain level of scope on what we want to do. I think, just like an artist, you have a toolkit, and now you have an idea, a concept that you want to paint, you would try to optimize around your toolkits. In that sense, there are no boundaries for the security audits for us, but at the same time, we have about 3 months. We have to prioritize what we can do. And like Ali was saying, a lot of tools, especially auditing tools, are, even if they're available, they're very premature. So there will be a lot of false positives you will come across. So trying to understand and explore into them, what makes sense, what doesn't make sense. It's a very painful process. And that's why what's working for some of the companies is a lot of manual process.
Yeah. To give Mohammed maybe a concrete target, you should be comfortable with the concepts of generics and traits, for example, in Rust. So those are advanced, relatively advanced concepts. You should be comfortable with those. And if you aren't, this is a perfect example of what we call trial by fire. This is not something we're going to teach or spend time on. This is something you are expected to catch on super quickly. So Enrico actually was telling us in the last meeting that these two advanced concepts are kind of like a flag post. If you have comprehended them, if you have reached a point where you understand generics and traits, then you should be comfortable with Suma, for example. So you can use those as a finish line flag post for you. Oh, okay. Now I understand generics and traits fully. That means I am in a good position to look into Rust.
All right, we have no more questions.
Excellent. That's we are right on time, I guess. Yeah. I'll leave it up to you, Nagu. If anyone, maybe you can ask the residents if they have anything to add before we close.
Yeah, if any residents have anything to add before we close for today, that would be great. And then Wednesday we are meeting. Before that, we'll share the link to the recording and slides. Anybody?
I think it's been great talking with you all, and I would encourage all of you to put your questions in Discord so we can answer them. And hopefully, we expect you to dig in a little more on Halo 2 and Suma. And yeah, see you all next Wednesday.
Great.
Yeah. Thank you,
Thank you,
Nagu.
everybody. Thank you, Ali.
everyone.
Thank you, residents. Thank you, everybody.
Thank you, Ali. Thank you, Naga.
Right.
Appreciate the session.
Yeah.
Yeah,
Right, see ya.
bye-bye.
Bye-bye.
Bye, everyone.